Okay, this is lecture 27, and we were discussing flame stabilization in the last lecture, and we were looking primarily at a simple burner, which is just a tube burner, and then we were trying to see why the flame shape changes, the flame height changes as you change the flow. So what we discussed last time is that when you are sending fuel air mixture through this tube, you may get a flame which looks like a cone but with a short height at lower flow velocities, and as you increase the flow velocity, the flame will give you smaller and smaller cone angles. So if you keep increasing, the cone angle can become even smaller, it can become like this. So this is the half cone angle alpha, which we sometimes write to relate the laminar burning velocity to the speed of the unburnt fuel air mixture. So we wrote SL equal to VU sin alpha, and if you can match your VU exactly to SL, then you may be able to even get a flat flame, but it's a very hard thing to do practically. Okay. And if your VU is more than SL, then of course there is sin alpha, which is SL by VU, so that the cone will give a half cone angle. Cone will give a cone angle, okay, and the cone angle will keep on decreasing according to this equation, because as you increase VU, VU sin alpha will always have to match SL, and as you increase VU, alpha will have to keep on decreasing, because SL by VU, which is sin alpha, that is actually, as you increase VU, that in fact keeps on decreasing. So that is alpha. So that's what we discussed last time. So what the flame is trying to do is to change its shape in such a way that the normal component of the flow velocity still equals the laminar burning velocity. So laminar burning velocity is a characteristic of the fuel air mixture, and it's trying to adjust its shape so that the normal component of the unburnt mixture velocity matches the laminar burning velocity. But we also discussed last time that this cannot go on indefinitely. As you increase the velocity VU, there will be a point where the flame will not be able to reduce its cone angle any further, and in fact the flame will get lifted. So the lifted flame situation is when you get a flame which is not anchored to the burner. If you look at this set of pictures, the base of the flame is very close to the top of the burner. So the top of the burner exit plane is here, and the base of the flame is very close to that. That is an anchored flame, that is a stabilized flame. This is not a stabilized flame, the one which I have shown here. Okay. This has a significant standoff distance from the top of the burner, it is away from the burner. So this is a lifted flame, and this is a lift off situation. So now this is happening when the fuel air mixture velocity is actually high compared to the laminar burning velocity. So what the flame is trying to do is, in that case it is trying to move away, and as it moves away, it is able to find another position where it can somehow match the normal component of the flow velocity to the laminar burning velocity approximately. So that is what it is being able to do. So why did it happen this way? The flow velocity is too high, but if the flame gets lifted, then the flow will tend to expand a little bit, and the effectively the flow velocity which is going into the flame will become smaller. Okay, because there is, if it gets lifted, there will be a jet effect, and then this jet will expand, and the velocities going into the flame will not be as high as it would have been if the flame was closer to the burner. So it is trying to make sure that goes a little bit away from the top of the burner, so that the flow velocity entering the flame is little less. Okay. In the process also what happens is there is some amount of air which will come into the mixture. So, it will tend to dilute the mixture a little bit, because there is a gap and there will be some diffusion of air here. So, it is no longer the same mixture which is burning out there. So, there is some dilution effect. Now, so this is the lifted off position. Now, lifted position is actually not very stable, in the sense that it is very delicate and it may stay there, or it may just somehow with some fluctuation in the flow may just get extinguished, may not survive out there, or it may move about that place. So, it is a very delicate flame, and lifted flames also result in some loss of fuel air mixture, because some fuel may go out from here, some air may come in. So, you may not be actually burning the same mixture that you initially intended to. Lifted flames also sometimes are noisy, and lifted flames are difficult to control. So, let us say that your purpose is to establish this flame on a burner to heat something. Okay. So, some flame you want to generate here which will heat an object. This object, let it be this object. Now, with an anchored flame, you know what you are doing, you are more sure of what you are doing, but with a lifted flame there is this chance that the flame will move about and it will not stay in place, or it may even get extinguished, because it is kind of at the limit of stability. So, lifted flames are typically not desirable. If you are a combustion engineer and you are trying to use flames to heat something, then you will not like to have a lifted flame. Okay. By design, we are not trying to get a lifted flame. If it happens, then it is better to change the burner design, change something, change the flow, and make sure that the flame gets anchored back again to the burner. So, it is undesirable. Lift off situation is undesirable. Now, what happens if you, from a lifted position of the flame, if you further increase the fuel air mixture velocity, then it might still remain in a lifted position for some more some higher values of the fuel air mixture velocity, but it cannot indefinitely do so, and there will be a point of time, there will be a situation where it will not be able to negotiate any further and the flame will get extinguished. So, beyond lift off, what we get is blow off. Blow off means it is getting extinguished. So, this is one kind of situation when you are thinking of starting with a flame which is a short cone, you increase the flow rate of fuel air mixture, then you get a flame which is like this. You increase it further, the flame still adjusts, reduces the half cone angle. So, the alpha reduces. So, alpha is much less here compared to what you get here, compared to what you get here, but it cannot indefinitely do that as you increase the fuel air mixture velocity. So, it gets lifted to some position. When it gets lifted, as I said, it is not a very desirable situation. So, this is something which we typically try to avoid, but let us also think about what happens if we increase the fuel air velocity further. It can get completely blown off, that is, its flame cannot find a position where it can even remain in a lifted state, even that does not happen. So, you get a flame which blows off, so it gets extinguished. Of course, you will not desire that, because once it gets extinguished, then you are sending out fuel air mixture without burning it. So, that is of course undesirable, it is very easy to see that. So, this is one aspect of flame stabilization. Of course, there will be another aspect of flame stabilization, that is when we think of reducing the flow rate of the fuel air mixture. So, let us think about a situation where you have an anchored flame, so flame like this, and you reduce the, now from this state you reduce the fuel air mixture velocity. So, it will tend to become like this. We are following the reverse argument of what we have been discussing before. So, it will try to now increase the cone angle, correct. Again, remember SL equal to VU sin alpha. So, it will do that, it will tend to become flatter, it will tend to become flatter as you decrease the flow rate. But then if you ask yourself, If I decrease the flow rate any further, then what happens? Then the flame will tend to move down. Okay. So, that is called flashback, and we understand that flashback is not desirable. Correct? Flashback is unlikely to be desirable. So, when is flashback happening? Flashback is happening when the flow velocity, that is Vu, is small, relatively small. Small compared to what? SL. Small compared to laminar burning velocity. So, we are looking at this balance, right? SL equal to Vu sin alpha. And if we say that we will keep on decreasing Vu, a point will come where Vu is smaller than SL, and then the mixture, the flame in that mixture will tend to move back into the burner, because it is typically like this. The flame, to be able to remain in an anchored position in the form of this cone, requires a certain feed of fuel air mixture. If you reduce the feed, then the flame has no other option but to travel back, okay, in order to survive. So, it will then will travel back, the flame will look like this, and it tries to heat the mixture ahead of it, and if it heats it, ignites it, then you get the flame here, that keeps moving. Then it becomes similar to what we had been discussing some time back, that of a flame traveling in a tube, isn't it? We discussed how flame propagates. We understood that flame is not a material surface, it actually heats fuel air mixture ahead of it, and then also transfers some active chemical species to it, thereby ignites it, and thereby it moves. So, it will have a situation where it can easily move down because you are not feeding the fuel air mixture. This is what is happening. So, we understood that there is lift off, there is also blow off, and there is also flashback. But broadly this is a situation, of course, but we have also should try to focus a little bit about how exactly this happens. Remember, in the last lecture, lecture 26, I said that if this Vu is uniform, that is, on the top of the burner, if you move radially, Vu does not change. Suppose that is the case. Suppose you have a flat kind of profile, right? Suppose you have a flat kind of profile that is uniform Vu. Suppose you get that, then you will get a sharp cone. This is what we discussed last time, because SL is typically one number. So, let us say methane air mixture at 1 atmosphere 298 Kelvin, this is about 37 centimeters per second. So, the 37 centimeters per second gets divided by Vu. Let us say if this Vu is 74 centimeters per second, then it is 37 by 74, that is sin alpha, right. But let us ask ourselves this question, are we likely to get uniform Vu? It is actually very hard to get that. You can't get that with a tube, because then it will tend to give you a more parabolic, more rounded velocity profile. If you have, instead of a tube, if you have at the top of the tube, if you place an orifice with a sharp edge, okay. So, if this is an opening with an orifice with a sharp edge, then that tends to produce a more uniform velocity profile. Okay. So, there is a particular orifice design which can give you a more uniform velocity profile, and then that will tend to give you a sharp cone. But of course, most of the time we are not talking about this sharp edged orifice giving you a uniform velocity profile and giving you a sharp cone. That is mostly not the case. So, if it is not the case, then what is it? Then let us work with the more expected profile of the velocity. Yeah.
Is there any particular advantage of having a flame shape, a nice cone?
No. There is no particular advantage. The question is there any particular advantages in getting a sharp cone? There is no advantage as such. We are just trying to understand what happens. So, that is why we are trying to understand the flame shape. So, we see a conical flame, but it is not exactly conical mostly. You have seen a Bunsen flame, it is not exactly conical, it looks similar to a cone. So, what I am trying to tell you is that if you are able to give a uniform velocity profile, then you are trying to get closer to a geometric cone, trying to get a cone which is sharper. Okay, it's not so rounded. But that uniform velocity profile is not very likely, so quite often we don't get that sharp cone. So the cone that you see is usually not a sharp cone, and we are trying to understand that better. Okay. So you will actually see that the cone is more like this, something like this, not exactly a sharp cone. And also it will be good to understand what happens at the rim. Okay, this is the burner top, so this is the rim. It goes all around. I have marked at one place because it's on paper, but it's all around, right? So it's here, here, everywhere. So what happens out there? At that place, actually, there's a flame anchoring mechanism. The flow velocity in this region is likely to be small, okay, because you are not going to get this uniform velocity profile. So there will be some boundary layer effect inside the tube. So there will be low flow velocity, the higher flow velocity at the center, and okay, close to the wall, the flow velocity is going to come down because of boundary layer effect. So low VU near the wall is expected. Low VU near the wall. What about SL? SL, I said, is a property of the mixture. So can we say that, okay, if it is methane air mixture, stoichiometric, pressure is equal to 1 atmosphere, temperature is 298 Kelvin, is it going to give 37 centimeter per second everywhere? Actually, we usually like to think of laminar burning velocity as a property, but we have to remember another fact, that it also changes, laminar burning velocity changes if there are losses. So the property that we are talking about is actually the adiabatic laminar burning velocity. That's a property. Our derivation was also for the adiabatic case. But here you have a mixture giving you a flame which has this base very close to the top of the burner. So it will lose some heat, lose significant amount of heat to the solid of the tube. So if you measure the tube temperature somehow in this region, you will see higher temperatures. So if you are doing the experiment at room temperature, maybe 300 Kelvin, it's possible that temperature in this area becomes 310, 320. Okay, so that's very much possible. So there is some heat loss from the flame to the tube. And if it is a long tube, then 310 here also can mean significant heat loss, isn't it? Because it's taking heat from the flame and it's transmitting that heat along the length. It's a long tube, so the burner overall doesn't get very much heated, but it's definitely losing heat. The flame is definitely losing heat. If it loses heat, then it's no longer the adiabatic laminar burning velocity near the wall. Near the wall, it's no longer the laminar burning velocity. We are thinking of stabilization as something which will happen when the laminar burning velocity is matched by the flow velocity. Now, near the wall, the flow velocity is low. Near the wall, the laminar burning velocity will also be low because of heat losses, and in fact, there will also be some radical loss. Some chemically active species may get absorbed in the wall, and there will be some loss. So because of losses, SL itself can come down. So SL comes down and VU also comes down near the rim, and it might just happen that both are low, but both approximately match one another. Then that is good news for the flame, because then the flame can stabilize itself on the rim. Okay. So if you increase the flow velocity, the velocity here, flow velocity in this region near the rim actually goes up, and then the flame laminar burning velocity is still low because it's near the wall, losing heat. So it tries to move up to some other position where the losses are less. So that is an advantage for the flame then. Okay, so the losses are less. Plus, because of this expansion effect of the flow, it's kind of a jet effect, so the flow velocity also comes down. So they match each other. So in a lifted flame also there is some approximate matching of the laminar burning velocity and the flow velocity. The flow velocity is higher, but the laminar burning velocity is also higher because the flame has moved out. reducing its heat losses to the burner. Okay, so this is a complex mechanism, but we have to keep this in mind that we are not going to get uniform flow here. Flow velocity is low near the burner rim, but the burning velocity of the mixture is also low. So, the burning velocity, because it is not adiabatic, it is actually not a property of the mixture at that location. Okay. So, this gives you some idea of how flames get stabilized. So, stabilization of flames is an extremely important issue for obvious reasons, because we do not want lifted flames, we do not want the flames to get blown off, and we do not want flashback. Remember, I discussed a couple of classes back that if there is a flashback, then the flame can travel all the way back. It can go to that mixer where fuel and air are getting mixed. So, there is a mixer where there is a fuel supply, there is an air supply. So, the mixture gives this fuel air mixture, and in case there is a flashback, and if you do not stop that flashback, the flame can go to the mixer and it can get a large volume which it can ignite. And if the flame travels fast somehow out there, then there can be a quick release of lot of energy, and it can lead to some catastrophic events, explosions. So, flame stabilization is extremely important. Now, when we design commercial burners, we actually try to take care of all these and operate the burner in a region where it will not flash back and it will not get lifted off. Okay, forget blowing off, not even lifted off. And we will try to take a look at actually a stability diagram. So, this is a stability diagram. All right. So, if you take a look at this, this has the gas input rate. This figure is also from Stephen Turns's book. This has a gas input rate on the x-axis. The gas input rate will mean the fuel air mixture coming out of the port. Okay. And plotted on the y-axis is the primary air, which is percentage of the theoretical. Okay. So, the y-axis terminology I have not discussed so far. It means that in this burner, you are sending fuel and air, and the air that you are sending with the fuel, you are calling that primary air. Okay, that is what it is usually done in combustion literature. And then that primary air as a percentage of theoretical is plotted on the y-axis. So, you may not be sending 100% theoretical air with the fuel, you may not be sending that. The combustion may be getting completed outside, I mean with the help of outside air or some secondary air coming into the flame. Okay. So, the primary air is the air which goes with the fuel, and that is shown as percentage theoretical. So, if you see 80% on that y axis, then that means that you know the fuel flow rate from the stoichiometric equation. You can calculate the stoichiometrically correct amount of air, and you take 80% of that and supply that 80% air through the primary port. But there may be some secondary port in this burner, or there may be it's using some extra air from atmosphere. Okay. Now, you will see that there are 3 curves. So, the one curve which you see here, it is a flashback zone. Okay. The flashback zone meaning on the right hand side of that curve which you see, you will not see flashback, and on the left hand side you will see flashback. Okay. Let us try to understand that. If you are on the left hand side of this line, that means if you are here, then your mixture flow rate is really small, correct? Mixture flow rate is really small. Do we get flashback when mixture flow rate is small or mixture flow rate is high? Small, because if you are high, if the flow rate is high, then you are likely to go into the lift off regime and the blow off regime, not towards flashback regime. So, it makes sense to see flashback when the gas input rate is small, correct. We can understand that from the figure. But why is that curve centered close to that 100% theoretical layer?
Air will also come and it will really make that mixture lean.
Yeah. So, what this curve actually tells you is that if you have primary air as 100% of the theoretical, close to 100% of the theoretical, maybe little less than that, then your flashback zone is the widest. Okay. That means if you have a velocity here which is this much high, then you are going to get flashback only if your air is close to 100, primary air is close to 100% theoretical. That means if you go up with the same velocity, you are not going to get flashback. If you follow the cursor that I am showing here, if you follow the pointer that I am showing here, with this velocity, imagine this velocity, with this velocity for 110% theoretical air, you are not going to getting flashback. With the same velocity, you are getting flashback for about 100% or maybe little lower than 100% theoretical air also. What is the reason? Yes. So, it is a fight between, it is a tussle between the flow velocity and the flashback and the flow velocity and the laminar burning velocity. Okay. So, the laminar burning velocity is likely to be highest when you have 100% theoretical air, close to 100% theoretical air. So, in that cases, you are in the danger zone. Your flow velocity is low. Okay. Look at the left hand side of the flashback zone. So, you will see that low flow velocity coupled with high percentage theoretical air, and high percentage theoretical air, as you pointed out, translates to high value of laminar burning velocity. If you get that combination, you are going to get flashback. So, you can avoid this zone. So, what people do is that they make a burner design, they do some experiments and prepare this kind of a stability diagram for a burner. Okay, this is actually for an industrial burner. Okay. So, you can avoid flashback. Very easy, you give flow velocity higher than what you get in this zone, then you will not get flashback. Okay. But there are other problems also, that is, there is this line here, and if you get high gas input rate, then there will be lifting zone also. All right. So, as you increase the gas input rate, you are increasing the flow velocity, and as you increase the flow velocity, this line dips down. Above this line, where my pointer is the lifting zone. So, the lifting zone, the extent of the lifting zone actually is increasing as we go more towards the right. More towards the right means higher values of gas input flow rate. That is understandable, because higher flow velocities will tend to widen the lift off regime, correct. And there is another one also which I did not discuss so far, there is an yellow tip zone. Yellow tipping actually is understood better in the context of non-premixed flames, diffusion flames. Okay. So, if you have a diffusion flame, then diffusion flames can produce soot, and the tip of the flame can show a lot of soot coming out, and that is called yellow tipping. Okay. And this particular burner, I do not have the details of this particular burner. This is some burner for which stability diagram is available. It is included in Turns's book, and that is why we are looking at the stability diagram. I do not have full details of the burner itself, but it may not be a simple tube, and in any case we are not doing 100% premixed flame, in the sense that we are not, see, 100% premixed would have been if you are sending all the air that is required for combustion along with the fuel. So, if you look at the stability diagram, you understand that that is not exactly what we are doing. We are sending, we are actually sending less than 100% theoretical air in some cases. And you will notice that if the percentage primary air that we are sending with the fuel is low, like 20, 30, 40%, then below this line we are going to get yellow tipping, that is soot coming out. Because if the percentage theoretical air that you are sending as a primary air, if that is small, 20-30% of the required amount, then it's actually not a premixed flame, it's more like a non-premixed situation. Okay, it's actually between a non-premixed situation and premixed situation, but low amount of air, low amount of primary air as percentage of theoretical will give you soot. It's becoming more like non-premixed flame, so it will give you yellow tipping. So when we talk about non-premixed flame later, you will understand this better. So looking at all these, if you have made the burner, if you have done some experiments, there is some information available to you, you are the combustion engineer, you are the designer, then you can get this particular stability plot, and it tells you that you have to avoid flashback, you have to avoid the lifting flame zone, and you have to avoid the yellow tip zone. So ultimately you have to be between these two lines primarily, and this is a good area because then the stability zone is wider. If you go too much into this, then the stability zone is actually getting squeezed, right. So you come into this zone, this is the stable zone area, flame zone, and this is roughly the design area. Okay. So this is one plot, actually one stability diagram, and this is taken from Stephen Turns's book, so you can also see this yourself later from the book. There is another one. So the first one, the one we just now saw, that was for natural gas air burner, and the second one which you see is called what is called manufactured gas. So this is for a manufactured gas. Now manufactured gas actually has some hydrogen. It has some other things, but it has got some hydrogen also. If you have more hydrogen, it is not surprising that you will get a wider flashback zone, correct. Again, if you look at this plot, this is similar to what you have seen in the previous plot, but all the curves have shifted, the zones look a little different, but still you have a flashback zone, you have a lifting flame zone, and you have yellow tip zone. So burner to burner, the curves, the appearance of the curves will change, and you have to locate yourself between these two lines and avoiding the flashback zone to get a possible design area, correct. So it's fundamentally, qualitatively, it's the same thing. So this second plot is very similar to the first one, but manufactured gas has some hydrogen, and you will see that the flashback zone actually has got widened. So now even with even with higher values of gas input rate, you can get flashback. So this comparison is useful only in the sense that okay, you have to be careful, mindful about the fuel that you are using. If you have fuel with hydrogen or something which burns very quickly, then SL is going to be higher, laminar burning velocity is going to be higher, and if laminar burning velocity is higher, then even for moderate flow rates through the burner, it might just travel back. Okay, so that's why the flashback zone is more expanded. Right, so this is our discussion of laminar premixed flames. So we discussed laminar premixed flames. First, what is its importance, and secondly, what is its most important property. So laminar burning velocity, we did a derivation for that. Then we looked at what laminar burning velocity depends on, pressure, temperature, etc., equivalence ratio. Then we looked at some phenomena like quenching, ignition. We also studied flammability limits, how flammability limits is determined, and finally today we have discussed flame stabilization. For obvious reasons, flame stabilization is actually extremely important and related to our understanding of quenching, for example, isn't it? And finally we now got, in terms of these plots, we have got something which is used in industry, stability diagrams for some burners. Okay, now we will close the discussion on laminar premixed flames and we will go to discussion of turbulent premixed flames. Now before we actually discuss turbulent premix flames. Couple of things. One is that turbulent premix flames are much more common than laminar premix flames. Laminar premix flames are there, of course, in small heating applications, for example, for heating glass or for heating something in the lab. Okay, small flames. Lot of heating applications. But if you want to actually have heating applications with high heating loads, or in engines, or in furnaces, large flames, fast heating rates, then you cannot depend on laminar premix flames. Then you have to go to turbulent premix flames. So turbulent premix flames are much more important from practical point of view than laminar premix flames. But we have a problem. Our difficulty is that this is the first course in combustion, and for us to understand turbulent premix flames will be more difficult. And to compound matters, there is no real easy theory to understand with regard to turbulent premix flames. Things are actually very complicated. Some theory, some analysis which can be presented in classrooms and which you can understand in 3 or 4 lectures or 5 lectures or 6 lectures, that's not easily available. Okay. So here we will discuss turbulent premix flames to some extent, but not do much analysis, but we will do some phenomenological study, in the sense that, okay, what are turbulent premix flames like, and what are different regimes of turbulent premix flames, what are the different kinds of flames that you get, what are basic characteristics, features, things like that. We will not be able to do analysis. Like we did an analysis and then we, for laminar premix flame, got a cell equal to square root of something, and then we got some expression for quenching distance, we got expression for minimum ignition energy. That sort of analysis we will not be able to do for turbulent premix flames. Now we will actually just take a look at one video, and we first take a look at this. Is about 1 minute, I think, and you can just observe this, and then we can see what it tells us. Same sort of picture, nothing much really changes, but please observe carefully. You will notice that the laminar flame surface is not really fluctuating much, it is more or less stable in space. Fluctuates a little bit if you look at the tip of the laminar flame, moves about a little bit, but the turbulent flame moves quite violently, isn't it? There is something also happening at the base of the turbulent premix flames, flame that you see, and this is, I think it is playing it again. This is taken at 300 frames per second. And then there is another one where we just look at the turbulent premix flames, but at 2 different camera speeds. FPS is frames per second. So the 300 frames per second video has been made by using a large number of frames. So there the camera is taking 300 frames per second, and then these frames have been put together to make this video. And the other one is for 60 frames per second. Okay. 60 frames per second. Same flame. Yeah. Same meaning comparable flame. I mean, they have been flame, of course, itself changes a little bit. So even if you set up the same flame, first you do 600 frames per second, then you do the same flame with 300 frames per second. We cannot say that 1 minute of the 600 frames per second is exactly the same as the flame. Flame itself would have changed maybe a little bit. But
in the carbon, in the 60 FPS,
yeah,
the diffusion zone that you can see, just just above that cone.
Yeah, yeah.
That part we can't see.
That glow is not very clear in the 300 frames per second. So 300 frames per second is peaking up actually individual flames, in the sense that if you notice, this is kind of blurred, the whole thing, isn't it? It gives you a glow. So with naked eye you are more likely to see something close to this, fine. Whereas if you take 300 frames per second, then you are resolving flame which is moving. Now what I mean by that is, a turbulent flame can be thought of as a superposition of individual flames. Okay. So what I mean by that is, this can be an instantaneous turbulent flame. This is the fuel air, this is the tube through which you are sending fuel air mixture at high velocity. Okay. So the actual situation is turbulent, but what I have drawn is one flame which is like a laminar flame, but this has been obtained at one instant of time. Okay. Suppose we are able to do that, then you see a flame like this. The very next instant it will change. Okay. The instant after that it still changes in some way. I am just drawing some curvy line, that is all. Okay. I am not using any logic to draw it in a particular way. But what is in fact happening is, if you can think of these as, this is as 1, then this is as at 2, and this as 3, if you say that, then it's like you at one instant of time you get 1, the next instant of time 1 becomes 2, like that. So one way of looking at turbulent flames is that turbulent flames consist of laminar flamelets. So one laminar flame fluctuates and changes into something else, and this thing is happening very rapidly. So we go from 1 to 2 to 3, like that, and this is happening all very rapidly. If this happens very rapidly, then you will get a blurred thing, you will get to see a blurred flame, right. So you will get to see, you will not be able to pick up, with naked eye you will not be able to, human eye does not have that sensitivity. So you will not be able to pick up these individual flames that I am drawing here. You will rather pick up something like this. Okay, you will pick up this whole envelope. So if you look at the low speed picture in the video, if you speak at the low camera speed, okay. So this frames per second is camera. Okay. So that that gives you more like a blurred image. So if you look at this part, see, this may be lot of flamelets which are dancing around and giving you this blurred zone. Okay. And here you are able to resolve these individual flames to some extent. That is why it gives you the impression that it is actually one flame or two flames which are moving about, correct. So if you compare the two, you will probably agree with me. Like in the high speed one, it does seem like with high speed you are able to resolve it into some flames, some individual flames which are moving about and giving you the impression of a large thick flame zone. So this is the whole idea, that we can think of turbulent flames also as juxtaposition, assembly of laminar premix flames. Okay. Turbulence by definition has these fluctuations, randomness, chaotic nature. That is why you get this, if you look at this one, you see this corrugated stuff which is also fluctuating and changing all the time. Okay. Compare all that to what we saw just a few minutes back for a laminar flame, and of course, you will agree that this is much more steady, it's quite well defined. Things are happening near the tip though, to some extent. The tip is moving a little bit, but otherwise it is kind of steady, otherwise you can give it a definition. The problem is here, what do you call the flame? Here, what do you call the flame, because the flame surface is continuously moving. So, this is a very hard thing that we are encountering now, and as I said, there is no easy way of studying turbulent premix combustion. So, going back to the discussion of turbulent premix flames, we are now just introducing turbulent premix flames. Now, in case of a laminar premix flame, you can have an area, you can properly define an area, and you can define burning velocity, and with the help of this, with the help of SL, with the help of rho u, you can define a mass flux, and you can multiply this by the area to get the mass consumption rate, isn't it? We had some time back written dmu dt as AF rho u SL, something like this, correct? We wrote it in terms of this, but there has to be a negative sign, correct, because dmu dt itself is negative, the unburnt mass gets consumed. So, we have done something like this. So, we had no problem with defining an area, but when you come to turbulent premix flames, suppose we want to do an analysis of turbulent premix flames, then we have to think about some turbulent burning velocity, just as we did for laminar premix combustion. Laminar premix combustion, we had this SL, because SL multiplied by rho u multiplied by area gave you the consumption rate. Consumption rate of the mixture is very important, because that multiplied by the heat of combustion gave you the power that the engine is producing. Okay. So, that is extremely important, but how do you do it for turbulent flames, because the area is going to be a problem. Which area? All right, because the area seems to be fluctuating all over the place. So, that is one problem. The other thing is that how do you at all define turbulent burning velocity? Turbulent burning velocity can be defined similar to laminar burning velocity, in the sense that it is that velocity with which the unburnt mixture moves into the flame relative to the flame, normal to the flame. If you can do that, right? You can say that, but then measuring turbulent burning velocity is also very hard, because if the area itself is moving about, then getting the velocity with which the unburnt mixture is moving into that flame zone is very, very hard. Whereas for laminar burning velocity, even though we did not discuss this, I think you kind of know that it is not all that difficult to measure it. At least you can get an estimate quite easily in the lab. I think in passing I discussed this, some of you have done this kind of an experiment in the lab, that if you have a laminar premix flame like this, and this is the axis, this we call an alpha, knowing fully well that it is not exactly a cone, not exactly a sharp cone, but still you can take a photograph of the flame, do an image processing of the picture that you get, and get alpha from a direct photograph. Or if you want to do a better job, you can use an optical method like Schleiden method or shadowgraph to get alpha, and if you get alpha, knowing the velocity here, you will know the velocity, right? Vu is in your hands, so you will know that, and since SL equal to Vu sin alpha, you can measure alpha if you have Vu, so you can get an estimate of SL. For turbulent burning velocity, it will be more difficult, because defining that area, the flame zone itself is difficult. The flame zone is now becoming, in case of turbulent situation, flame zone is becoming like this, okay, some thick zone. Which area, where to take the velocity, okay, is there a cone, we do not know all that. So, this is all going to be somewhat difficult. So, as I said, we will take a phenomenological approach. Okay. What does this mean? That means that we will not do an analytical approach. We will not write equations, conservation equations trying to solve. It will be too hard for us to do that. Phenomenological approach means phenomenon is like what you observe, things which you observe. Um, there is a phenomenon of flashback. There is a phenomenon of liftoff. There is a phenomenon of flame getting stabilized on a burner. Okay, and a phenomenological approach is based more on observations and some empiricism. That okay, you observe and then you say that okay, maybe for if the flame thickness is this much, then the turbulent flame will be in this regime. If the flame thickness is compared to the turbulent length scales in the flow, if it is larger, then this will happen. If it is smaller, then something else will happen. That sort of description. So, phenomenological and empirical approach is what we are going to take when it comes to turbulent premixed combustion. Now, we are running out of time today. So, we will start taking this up tomorrow.